Good morning, everyone. So we are recording now. All right. So last time we completed our discussion on a primal dual algorithm for the shortest path problem, right? Are there any questions or concerns regarding that? Anything that requires more clarification? Okay. So if not, I just want to make a couple of comments. So let me ask you the following. Did we actually need duality theory to get the algorithm? Or do we actually need duality theory to prove the correctness of the algorithm? Did anything really rely on duality theory, or was there a way we could have bypassed duality theory, linear programming duality theory? Right. Yeah. Right. Yes. We used complementary slackness. We used right, but we use the easier side of complementary slackness. That if the conditions hold, then the solutions are optimal. We didn't actually use the other direction of complementary slackness. Right. Right. So we actually don't need duality theory for the correctness of the algorithm. We didn't actually use duality theory in a certain strong sense, right? In assignment 5, you already proved that the labels for the ST cuts, sorry, assignment 1, my bad. In assignment 1, you had already, in exercise 5 of assignment 1, you had already proved that if you have these kinds of labels for the ST cuts, then the sum of the labels is a lower bound on the cost of any ST path, right? And in the second part of that same exercise, part B, you proved the complementary slackness conditions for this special case, right? So in theory, we could have just skipped linear programming duality. And we could have directly done assignment 1, problem 5, exercise 5, and immediately seen this algorithm, right? So why did we do duality theory? Does everybody agree with this so far? Right? Everything we used for designing the algorithm and whatever we need to prove the correctness of the algorithm was already done in assignment 1, exercise 5. Right. Whatever arguments you use. But we had the results. Right. That is one answer. Any other comments? So why do we need duality theory? Yeah, so essentially what Madhav said is the thing. So basically, where did those labels come from? So when you did assignment 1, exercise 5, you must have wondered, when on earth do these labels come from? How did anyone come up with this idea of putting labels on the SD cards? The same thing with matchings. In the lectures we discussed, reducing a certain integer from every edge's cost. I think I might have put something. Yeah, I forgot now. Yes, yes, minimum cost perfect match, right? So the point is, where do these ideas come from? And sure, one could have found them in some more ad hoc fashion for specific problems. But LP duality gives you a unified framework for looking at all of this. They are not just arbitrary ideas, they are actually the dual linear program. So there are cases where people found these results using combinatorial arguments like you did in assignment 1 exercise 5. But then later people realized that this was nothing but a special case of LP duality. So when you view things through the lens of LP duality, it gives you a better perspective. You don't feel that these labels are, you just pulled it out of a hat or something, right? You see some rationale behind why these labels are defined the way they are defined. Right? So that's really the reason why LP duality, viewing everything through the lens of LP duality, gives you a unified framework, and you can apply that same framework to other problems. Right? You don't have to pull things out from a hat. Make sense? Okay, so that's just a comment I wanted to make before we move on to minimum cost perfect matches. So let's see. All right. So our main goal, which we won't get to today, is to see a primal dual algorithm for minimum cost perfect matchings in all graphs. Right? Okay. So we will get to that eventually. It might take us quite a few lectures to get to the final goal, but we will start step by step. Right? So recall that in the shortest path problem, there is an underlying graph theoretical problem, which is finding an ST path between any two vertices S and T, right? And on top of that, there is this optimization variant is to find the shortest ST path. But finding an ST path is easy, right? You just apply BFS or DFS. That's it. However, here, even the problem of finding a perfect matching is not that easy. How do you find a perfect matching in a graph? Right? So we'll first address that problem. Right? So the first goal is to answer the following question: how to find a perfect matching in a graph. And in fact, as I mentioned last time, in most problems related to matchings, bipartite case turns out to be significantly easier than the general case. So in fact, we are going to look at an even easier thing. All right, so we are going to first focus on bipartite graphs. All right, so how do we proceed with this? So let me just remind you of some things. So let's recall a few things that we have discussed in module 1. So we discussed Hall's theorem, right? So let's say you have a bipartite graph G, U, W. So U and W are the color classes, right? So you can think of U as being the black vertices and W as being the white vertices. I'm changing the notation from AB because we are using AB for lots of other things. So let's say this is your bipartite graph. And let us assume that the cardinality of U is equal to the cardinality of W, because otherwise, of course, there is no perfect match. And so Hall theorem says that the graph G has a perfect matching if and only if certain types of sets do not exist. Can anyone tell me what is that? Okay, so what is S? Okay, Yeah, and what do you want between n of s and s? What could the problem be? So you want s to be in some problematic situation, right? Think about it. Yeah. N of s should be less than, right. So you don't want sets like this, or you want sets like this? You don't want sets like this. Right. So the graph has a perfect matching if and only if for every subset of the, let's say, black vertices, the neighborhood of S has cardinality at least the size of S. Right? If you have a set which doesn't satisfy this, then you cannot match all the vertices in S because you have fewer neighbors. So how can you match all of them? In other words, equivalently, G does not have a perfect matching if and only if there exists a set which violates this condition, right? And such sets are what we are calling deficient sets. Okay, because the number of neighbors, they are in deficit in some sense. Right? All right. So, all right. So this already tells us that, so we are going to be given a bipartite graph GAB, sorry, UW, right? And our desired output is going to be either we find a perfect matching or we find a order deficient set. Right? So either perfect matching M or a deficient set. And we can insist that the set is in U. It doesn't really matter. U and W are interchangeable, of course. All right. Okay. So while we are focusing in the lectures on finding a perfect matching, whatever we are going to discuss can be generalized to finding a maximum matching. Okay, that might appear on your assignment 5 or something. I'm not sure. So I'll just mention here that the ideas can be generalized to finding a maximum matching. And notice that if a graph has a perfect matching, then maximum matchings are the same as perfect matchings for that graph. Okay, so does anyone remember a necessary and sufficient condition for a matching to be a maximum matching? No M-augmenting paths, right? So that is Berge's lemma. For any graph G, it's not restricted to bipartite graphs. For any graph G and matching M, M is a maximum matching if and only if the graph G does not have an M-augmenting path. Let's do a quick example to recall the definition. Right, so let's say if this is your graph, and let's say I change the color. So let's say this is a particular matching, right? So is this maximum? No. Okay. So let me just call things V0, V1, V2, V3, V4, sorry, V4, and V5. Okay. And what is an M-augmenting path here? Right. So if it is not a maximum matching, you need to give me an M-augmenting path. No, we don't need any such things, right? Okay, 1%. V0, V1, V2. Can you complete it, Varun? Okay. I thought of something. Okay. V0, V1, V2. Now where should we go? V5, V3, V4. Right? So let us look at this path. Maybe I'll just put it in green. Right, so this is the path V0, V1, V2, V5, V3, V4. Observe that the alternate edges V1, V2, and V5, V3, they are actually edges in your red perfect matching. The other edges V0, V1, V2, V5, and V3, V4, they are not in your matching. And in particular, these two vertices are what we call exposed vertices with respect to the given matching. So if my matching M is the red color matching, right, then V0 and V4 in particular are M exposed vertices. And so I can just take the symmetric difference of the current matching with the edges of this path, and that will give me a matching of one bigger size, one bigger cardinality. All right. So the main goal is going to be, so the key sort of idea for any maximum matching / perfect matching algorithm is to find M-augmenting paths repeatedly until you can prove that they don't exist, at which point you declare that you have a maximum matching, or depending on the situation, a perfect match. Okay, so the key idea is always to repeatedly find M. Well, yeah, M will always be our current matching. So with respect to the current matching, we want to keep finding M-augmenting paths until we can find a certificate, some argument that such paths no longer exist. Right? So this is the key idea for any maximum matching algorithm. All right. Okay. So for the rest of this lecture, I just want to do some examples, and we'll probably formalize things tomorrow. Okay. On Wednesday. All right. So let's change the page. Okay. So let's start with some examples. So okay, so let's say this is our graph, and let's color the vertices. So these vertices are black, and the others are white. And let me give them labels. So okay, so this is U1, U2, U3, 4, 5, and 6. Okay, and there are the others, W1, W2, 4, W3. Okay, so that's our given bipartite graph with color classes U and W. So these are the black vertices and these are the white. Okay. So why do we need to do something so complicated? Can't we get a simpler algorithm for finding maximum matchings? Is that rather than going into all this M-augmenting path business and all, can we do something more? Sorry? Right. And can you relate this to something you did on assignment 1? A very simple technique fails. What is that technique? The greedy, right? The greedy technique fails for matchings for the simple reason that maximal matchings and maximum matchings do not coincide. And greedy will find you a maximal matching, not a maximum matching. However, you did prove in assignment 1 that maximal matchings are not too bad. They are, how good are they? Half. So if the maximum matching here is size 6, because you have 12 vertices, so it would be a perfect matching in this example, then a maximal matching would have at least 3 edges. Right? So okay, so we can start with a maximal matching, right? Finding a maximal matching is easy. Just pick any edge, delete the 2 vertices, pick another edge, right? Keep doing this. So let's start with a maximal matching. Of course, you don't need to do that. You can just start with empty and then there will be M-augmenting paths, but that's kind of single edge M-augmenting paths are kind of a bit silly, right? So we can start with a maximal matching to make it more interesting. So let's okay. So let me pick 3 edges here that comprise maximal matching. So let's say the maximal matching I find in a greedy fashion is this one. Why is this maximal? Can you give me an argument using stable sets? Sorry. Sure, you cannot add any more edges. Can you phrase it in terms of stable sets? what are the exposed vertices? Supposing this is my M. Okay. What are the M exposed vertices? W3, W5, and U3, U4, and there is more, right? M is all the three red edges. Yeah, all the three. Yeah, yeah. U6 and W6. Okay. So just to be clear, M is the three edges that I've drawn in red. U2, W2, W1, U5, and W4, U1. Okay. All right. Thank you. Okay, so that's our matching with three edges, and those are our exposed vertices. What do the exposed vertices comprise in this graph? It's a stable set, right? So if there were any edges there, you could have added it in the matching. Right? So just one way of looking at it. Okay, so this is a maximal matching because we can't add any more edges to it, right? That's right. Yes, yes. All the neighbors of the unmatched vertices are matched vertices. Yeah, that's also right. Okay, so we have a maximal matching. So we can't just apply the greedy algorithm anymore to make it bigger. So now we need to do something more fancy. And that more fancy thing is the idea of finding M-augmenting paths. Right? Okay. So, but we want to do some systematic way of finding M-augmenting paths, right? So the question is there a systematic way of finding M-augmenting paths? Okay. So let's go back to finding paths. How do you find a path between two vertices S and T in a graph? BFS or BFS? Okay, great. What does BFS or DFS construct? It constructs a tree in particular. It will be spanning if the graph is connected, right? So what you are doing is, in order to find a path between two vertices, you are constructing a tree. Okay? You're going to do something similar here. Now we want to find an M augmenting path. We are going to find, we are going to construct a special tree, which we are going to call an M alternating tree, which will become clear as you see how it is done. Okay, so we are going to do something very similar. So just like finding paths, finding regular paths, we will construct a special tree. And this tree will be called an M alternating tree. All right. So we want to find a path between two vertices that are both M exposed, right? And in particular, we want the path to be alternating with respect to M. So when you do BFS or DFS, you start at a certain vertex, right? You think of that as your root vertex. And then you have a tree rooted at that vertex. So where should we start? Where should we root our tree at? One of the exposed vertices. Exactly. So, all right. So let's construct a tree rooted at one of the exposed vertices. Okay. Anybody wants to pick a exposed vertex? W3. Sure. We'll start with W3. Actually, can we pick one from U, because then the set we will get, deficient set will be from U. So can you pick one from the black colored vertices? Doesn't really change anything. U6? Okay. Of course, in reality, it doesn't change anything, just because I want to stay consistent with the deficient set notation. So let's start with U6. All right. Okay, so because we have a tree and we are going to have a rooted tree, we can also assign levels to the vertices. Right? So I'm going to call this level 0. Okay. Now this is an exposed vertex, and the paths we want to find, we want them to be alternating. So what are the neighbors I should be looking at? I mean, in fact, right. In fact, in this particular case, all the neighbors will be covered or unexposed vertices, right? Because our matching is maximal. So in the very first level, you won't find an exposed vertex because we started with the maximal matching. But in level 3 or level 5, it might happen. Okay. So let's start with all the neighbors. And in this particular case, they will all be covered vertices. So the neighbors of U6 are W1 and W4. Right? Okay. So now we have reached level 1. What should we do at level 1? Okay. But should we consider all the vertices, or what should we do? Okay, so we'll get black vertices in the next level. We may or may not. We may or may not find an M-augmenting path. Notice that in this particular case, W1 and W4 are already covered. And we want to make sure, so here is the property we will try to ensure. In this tree, we will try to make sure that all the paths starting at the root and ending at any vertex will be M alternating. Okay, so this is one of the properties we want to do, right? So this tree, one of its properties will be the following. Every path starting at the root will be an M alternating path. Okay. So now at this odd level, so we are now at an odd level, level 1. Which edges should we consider? Should we consider the matching edges or the non-matching edges? We want to consider the matching edges because we want to make sure that all paths in this tree starting at the root are actually M alternating paths. Okay. So at this level, we are going to only consider the matching edges. Okay. So let me change the color here. And what are the matching edges? W1 goes to U5. Okay. And W4 goes to U1. Okay. I won't explore anything else. I will just explore the matching edges at this point. So this is U5 and this one is U1. All right. Now what should I do? Now can I take matching edges at this point? Right. Right. At this point, we anyways can't take the matching edges because the matching edges at those two vertices are already part of the tree we have constructed. So we can look at all the edges at this point and see what we get. So let's look at U5. Do I see some good news here? Look at the neighbors of U5 and U1. Okay. W6 is one of them. W5 is one of them. Right. But what's good about these neighbors? If you look at these two neighbors of U5 and of U1, so I'm not looking at the intersection of their neighbors. I'm just looking at all neighbors of U1 and all neighbors of U5 that are not already in our tree. So what is so good about these neighbors? Right, they form an M-augmenting path. You take any of these you like, and you get an M-augmenting path. Right. So if you are at a even level, if you are at any even level, and you find a neighbor that is already exposed, then you start from the root and you get to that vertex, and you will have an M-augmenting path. Right? All right. So let's just do that. So let's take any neighbor we like. So we will, in particular, I can take, I don't know, W5, I don't, and this is an M-augmenting path. So this is our path. Okay. Good. So we can take the symmetric difference of the current matching with this path. Let me call the path Q. Okay. In fact, it's the first augmenting path we have found. Let me call it Q1. Okay. So the new matching is going to be M symmetric difference with Q1. And so what does that give us? It gives us all the previous edges that were already there and that are not in this path. So we get U2, W2, W4, U1. And instead of this edge W1, U5, we are going to take the other two edges, U6, W1 and U5, W5. Okay. All right. So let me just make a copy of this. Oh, that's not how it works. Selection. Oh, I see. Okay. All right. So okay, so we included U5, W5, and we included U6, W1. So we have a matching which is bigger by one more edge, right? And now we can repeat this process. Right? So let's just do one more step and hopefully we can finish it after that. So let's build our tree again. Anyone wants to pick a black vertex which is exposed? U3. Okay, let's start with U3. Okay, and let's look at all the neighbors of U3. W4 and W2, right? That's it. Now we are at a odd level, so we are just going to take the matching edges. We're going to get matching edges here. I assume W2 and W4 are both covered. So we get, sorry, which one is this? U2, and this is U1. Okay. All right. And at both of them, U2 or U1, the only neighbors you see are W3 and W6, which are not already in the tree. And they are both exposed. So you can pick whichever you like. You could pick W6, for example, and increase the size of the match. Right? So you can include W6 here, and this would be our augmenting path. Right? So let's just finish the whole thing. All right, so now our new matching, and I'm going to just make changes here in this drawing. All right, so we are throwing away W4 U1, and we are including two other edges in its place. And those are U1 W6 and U3 W4. Right? And let's repeat. I think it's going to be the last step because we already have a matching which is as big as it can be except for one more edge. Right? So either we will find a deficient set or we will conclude that this is we have a perfect matching in the graph. So, okay, so where do we start now? Well, we are starting at black vertices. So for the sake of consistency, let's start at U4. We might end at W3. So let's start at U4. Okay, and let's look at all the neighbors. Well, they are W2 and W4. Right? We are at an odd level, so we'll only consider the matching edges at this point. So we get two matching edges. And what are the ends of them? U2 and U3. Okay. All right, let's just observe U3, what's happening. So U3, for example, its only neighbors are W4 and W2, which are both already in our tree, right? So we can't grow the tree anymore on that end. However, U2 has neighbors which are not in the tree, right? So we are going to explore all the neighbors of U2 which are not in the tree. So you get W3, which is already exposed, so you're done. You don't need to look at the other neighbors, right? So if you find an exposed neighbor at an odd, when you are at an even level, right, then you have an augmenting path. At the odd levels, you will always have matching edges. You only take those matching edges in your tree. So here we can consider W3 and we get this augmenting path. And now we throw away U2 W2 and replace it by the edges U4 W2 and U2 W3. So let's throw away this edge. So we get U4 W2 and U2W. And that in this example is a perfect match. Right? We don't have exposed vertices anymore, so we stop. Clearly, at this point, we have a perfect match. All right. So found perfect matching in this case. And that is, well, I won't even bother to write it down. Just put an arrow. Okay. So this is, of course, one way you terminate the algorithm. Okay. So when you can't find a perfect matching, you must be able to get a deficient set, right? And that should also happen from this tree somehow, right? Okay. So let me just do one quick example, and we might not complete it today. So let's see. Okay. All right. So maybe you all can do it yourself, and we can just quickly go through it tomorrow. So these are all back vertices, and you have U1, U2, U3, U4, and W1, W2, W3, W4. Okay, and well, I can give you a maximal matching. Maybe I'll just leave it as an exercise. Yeah. So I'll just say do it yourself or try it yourself. We'll do it in the next lecture quickly. So find any maximal matching M and run the algorithm we discussed. We did not formalize it, but I hope the discussion was clear enough that you can formalize it yourself for now. Run the algorithm we just discussed. And find either a perfect matching, which should be easy, or a deficient set. And in this case, I want you to find it using the last M alternating tree. Right? So there is a systematic way of getting a deficient set as well. If you don't find the M-augmenting path by this construction, then you will be able to argue, or in this case, just find using that tree a deficient set. Okay? And in the next lecture, we'll complete this example and we'll also formalize the algorithm, but formalizing it is fairly straightforward. I think you can all give it a shot yourself. So maybe this is 1 and 2, try to formalize the algorithm. Okay, and in the next lecture, we'll finish these things and start with the minimum cost perfect matching for bipartite graphs. So we'll be looking at the dual, complementary slackness, and doing the same kind of things. The only good news is that now we already have an algorithm for finding a perfect matching in a bipartite graph. So in that algorithm, we will need it as a subroutine. Okay. No, we need. So, what is the main difference between bipartite and non-bipartite graphs? It's the presence of what kind of odd cycle. So, the main problem is odd cycles. So, there is an idea related to how to deal with these odd cycles. Right, so, we will see that. Some of you may have seen in your previous courses, I'm not sure. But yeah, if you haven't, we will see that. It was a major breakthrough back in the day, 1965. Okay, cool. Any other questions or concerns? Anybody in the call? All good? Okay. All right, so I'll stop recording. I'm still here for another 5-10 minutes if there is any discussion required.